All right, so in this set of slides, we'll be looking at spatial operations, okay? And by spatial operations, I really mean convolution, which would be the way of, how you filter a picture and how basically you blur pictures or you find edges in a picture. And this is one of the most important aspects of image processing, so just make sure we get it right. And we're going to see that from the prism of using the same kind of notations we've seen in signal processing. You've seen that in 3C1, is it? Or all stuff with the Z transform and all these nice notations. Now, don't worry. There's not much maths as such involved after that. It's more kind of like a convenient framework that people use as well for 2D imaging. Right, so we'll start with the delta function, just a few notations. So remember the delta function, well, it's not really actually a function, but it's just defined as being plus infinity at a particular sample, and then be 0 otherwise. And really, it's only defined through integration, okay? So in fact, delta function is really a distribution. It's not really a function, but you know that, okay? So you define that delta function as, so if you have a function f, so that'll be your picture at two locations, so y and x. So y and x will be your coordinate system, okay? So you address your picture in grayscale, okay? So forget about color here. So we have a picture in grayscale, f of yx, and if we want to access a particular pixel of that function or sample that function at a particular location, and then we can use the delta function through integration. I say that the integral from over xy of delta of y minus capital Y, x minus capital X of f of yx is your sample at that position. So nothing new there, just there in the slides to kind of remind you of the notation, all right? The discrete version of that, so that was in continuous version, okay? So f was supposed to be your underlying signal, if you want, like the picture as it is, the physical reality of your picture, okay? And so this is the way you sample it. And if you're in already in a discrete version of that, so you have this time pixels, okay? So your f is already sampled. Then I'm going to call that function. I'm going to access f with square brackets, okay, by notation, okay? So continuous notations like curly, round brackets, okay? And discrete notations would be square brackets. Okay, so I said again, in the previous slides here, f is a continuous entity. Okay, so that's the light field, if you want. And that's what kind of your sensor does. Okay, so your sensor will sample that light coming to it. In this case, f of square bracket of hk is your, it's already you're accessing your pixel in your picture, okay? And that is, if you want, that's at the point where you actually have that in your program. So if you're in MATLAB or Python, whatever, what you have is notation this, and you have square brackets, and think of that as just a way of accessing your pixel in your array. And in this case, the delta Dirac function would just be 1 when you're at 0 and 0 otherwise. And the sampling, well, it's not really sampling, but the operation this time was the summation instead of integrals. Okay? So two versions, one the continuous, one is the discrete version. Right, so we come to, in what you've seen last year was linear time invariant systems. Okay? So that allow you to do all sorts of things, including Fourier transform and so on. Now, here we work in 2D, so there's, if you want, an extension of that, okay? But we don't call that linear time invariant because there is not really a notion of time, okay? So more a notion of space in this case. And so the equivalent is, we call that the linear shift invariant system, okay? So You just swap time by shift, and you'll be good. So similarly, okay, so all that is just extension of what you've seen to 2D. So the first aspect is the linearity. So the output of your system should be linear. So if you have, so let's say your inputs, so we're looking with discrete systems here. If you say you have two inputs, two signals, x1 and x2, okay, so basically two pictures, okay. And if you take a linear combination of these two pictures, which basically means you blend the two pictures together, okay, so you see a bit of both on the same picture, then the output of your system should be as well a blend of the output of the two pictures taken separately. All right, so that's kind of the definition you had for linear time invariant, but extended to pictures, and there's not much else to say about that. Okay, so linearity, you have a linear system basically involved there. And the second aspect is the shift invariance, okay, by opposition to the time invariance. And basically it means that so you have a process that transforms x into y, and then if you shift x, then basically the output of y should be shifted accordingly. All right. So if you have a picture and you translate that picture by some amount x and y, so you just translate that picture, then after you applied your linear shift invariant system, then basically you obtain the same results that you would have got without the translation, but translated this time. Right, so there's two aspects of the theory that just direct map from what you've seen in with linear time invariant systems. So linearity and this time shift invariance. So you can. So some notations on how you're going to note the systems. Okay. So basically, you have two types of notations that are that we'll use regardless and depending which one is more compact. So the first one is the following. Okay, so with access the tables as indexed by the square brackets. Okay, so you say in this case the output of my system I'm looking at defining is a linear combination of different points in my input picture, and but I reference here h and k and just using other neighboring points. So basically, this point would be the point on top of the current pixel. This on the left. This point would be the point on the right, and so on. This is another notation where you use instead of indexing your pixels with these square brackets, you can use actually a subscript. But that's the same. It's a bit more compact. Right. So just looking at what this. Just wanted to make sure we agree on that. All right, so we had something like that. So just making sure I'm happy with that. Yeah. So basically, what this linear system does, okay, there'll be called a convolution, but basically. What you have is a number of sites, that are just your pixels coordinates in your picture, and you say this is coordinate hk, and I'm going to say that the output of that coordinate hk is the input pixel at the same location minus the average of the 4 neighboring pixels. Okay. All right, so you can identify each of those. So this particular coordinate would be this one, and this one will be this one, and this one will be the north, and this one will be the south. Okay? So it's kind of very similar to what you've seen with 1D filtering operations. Here we just define a 2D filtering operation where we say the results of my filter will be a linear combination of my neighboring pixels. Okay? So that's the kind of operation we're looking at. Okay? All right. Now, obviously, we have an issue at boundary conditions, okay? Because here we're trying to access pixels that are on the left or right of the current pixel. So obviously, if you're at the corner of a picture, then you don't have access to that particular value here. So you need somehow to deal with what we call boundary conditions. Okay, and this is a boring but necessary problem to deal with, because when you deal with pictures, you might feel like, well, boundaries are not that big, but they exist nonetheless. And sometimes your picture becomes very small, and the boundaries actually become bigger than your picture. So what you do at the boundary needs to be defined precisely. There's like different types of strategies available. So if you say here, this is your input image, okay? So this is a 3x3 picture, so very small, and whose pixel values are 1, 2, 3, 4, 5, 6, 8, 7, well, anyway, 1 to 9. And you can say, so if you have different choices, either you repeat the values, and so they're based this way. So you have here. So I'm just going to extend by 2 pixels on each side my picture, and trying to say, basically trying to extrapolate. Okay, so you're trying to extrapolate what the picture should be outside of its natural boundaries, and you say, well, the values here are not defined, but let's try to find a reasonable extrapolation algorithm to say this value could have been this value. Okay. And so the first one, you just repeat the values, last value you can see, okay? So if the value at the border is 4, then you just repeat on that row 4 all the way to the infinity. And same here, if it's 6, you repeat 6 forever, okay? You can do reflection. So you say, well, if you're going 4, 5, 6 here, then you're going to, the next value here, it's going to be the one prior to this one, okay? So you're trying to, you say then it's 4 is here, they kind of have a mirror, okay? So the boundary acts as a mirror on your picture, you're just trying to extend this way. Zero padding is very useful if you're using neural nets, or more generally, if you use any kind of filtering that kind of tends to make your picture mostly zeros, okay? So here it's very simple, you just say any value outside of the boundary is just 0. And the last one is just a repetition of your picture. You just tile your picture multiple times, and then you can access any of these values. Now, each of these strategies is valid, but it really depends on what you want to do. I'd say repeating the value is probably the most common strategy. All right, so sorry. Okay, so we'll look briefly at convolution and stop here. So as with linear time invariant systems, we have convolution. So who is familiar again with convolution? You've seen convolution, right? Is that fresh in your brain? Okay. So we've just seen a convolution here. It's just a linear combination of your neighboring samples. Okay, that's how you define it. You say, I have my current pixel or my current sample in my time series, and I'm going to say that my output is defined as a linear combination of my neighbors. Okay, so it's all defined on what a neighbor is. So it's kind of a you define basically neighboring relationships. And so in 2D, this is what you get. Okay, so you say the output of my convolution is a double summation. Okay, now it's double summation because you have 2 dimensions. You have to go through the x and all the y's. Okay, of your initial picture, so that's I, and some kind of offset of some kind of weights. Okay, and P basically defines what your links between neighbors are. Okay, and so this is the one going back to this one. Okay, so your P's, your weights are this one. So minus 0.25 is the link you have between hk and h minus 1k. All right, so that's kind of weights that's defined between this coordinate and the coordinate on the left, and say that's my weight here. So when you're looking back at the equation here, this is the value of the pixel you're going to use, and this is the weight in your linear combination of your neighboring pixels. So this symbol here, the circle with the star, is the usual notation used for discrete convolution, but sometimes people just use the star. Okay. Right. So let's see. Do we have pictures of that? I'd like to see more examples of that. Yeah. Okay. So this is the kind of examples you have. So on the top left, you have the original block of your picture, and here we do a convolution by a convolution mask. Okay, so these weights we have between the neighboring pixels, usually they're not defined over a very large region. They're actually defined only over a few pixels here and there. So usually the notion of neighbors, like you only define that for neighbors that are not too far away from you. Okay, so in this case, we kind of define that for neighbors. So the central neighbor would be this pixel here, the center, and all the weights, all the numbers here. Basically, it says like we're going to take pixels that are plus or minus 3 pixels away from me, and I'm going to just average them. Okay, so I'm going to look at, I do a weighted sum over a 7 by 7 window, or plus or minus 3 pixels around me, and I'm going to average all these pixels, and that's going to give me the results here. And when you apply that for every single pixel, so which is what your convolution does, then what you get is a blurry picture. Okay, so typical effect on Photoshop. And you can apply different types of blur. So here we're using different weighting schemes, but this is what you get. More interestingly, when you apply convolution, you use different weights. Okay, so here what we're doing is we're taking the I might be wrong here, but we're taking the pixel on the top minus the pixel, so the neighboring pixel on the top minus the pixels, no, sorry, you're taking the current pixel minus the pixel on the bottom of you, okay? And what you obtain here is a picture, and so I've changed the color scheme here, so I just offset by 0.5, so basically every single pixel that's gray means actually it's a value of 0. Okay, so the output of the system is 0. And a value of 0, so when you see gray, that means that there's no difference between my current pixel and the pixel below me. Okay, so there's no change really between the 2 pixels. So if you see a uniform area where, like say, the sky or the sand on the beach where there's nothing really going on, then you would find that all the values here are 0. Okay, so because there is no change. But as soon as you see a change which would be vertical, okay, so you see, so you go along a vertical line and you see a big change, then it will be either picked up as being very bright, so a high value, or very dark as a negative value. So see, that's interesting because it means you can use this kind of simple filter operation as a way of picking up edges and so on. You can do the same for the x-axis. And coming back to the filter, we kind of apply like the operation, taking here the average of the neighboring pixels minus your current position. You get this kind of textured operation where you kind of trying to retrieve all the edges in your picture. Okay, so the output of the filter will be 0 if there is no edge whatsoever, and it will be non-zero, so either positive or negative, depending whether you have an edge or not. Right, so we need to come back on that. So, so just to give you an example, okay? So I write down here the code for convolution. So, I mean, this is again your definition for the 2D convolution, this is something you will have quite a lot in MATLAB. This is what you can do. Okay, so you define your picture here, and then this will be your 1, 2, 3, 4, 5, 6, 7, 8, 9 as defined in the slides, and you can define your weights this way, and then you apply the convolution function, and basically the convolution functions will actually compute that per pixel. Okay, so you don't actually have to write the code for that, and and that'll be simple. Right, so I'm trying to find if there's something there for that. There's none. So an issue you will find, okay, is the same way we try to have, we might have to access points that are outside the image domain. The question here would be what to do with the output size of your picture. And I'm not going to go into too much detail here, but basically you have, again, some choices. Either you say, as long as I can latch onto, like as long as one of the values from the original picture is defined, then I should output a value for G. And in which case, the effect of it will be that your output picture will be slightly bigger. Okay, see if you have, going back to this graph, so here I'm outside the original coordinates of your image. So if you want coordinate, I don't know, it's like -1, 4. Okay, so you're outside the picture boundary. But one of these neighboring values from 1 is, so the lower right one, this one is actually part of the image domain. So you could think that, okay, if I apply convolutions, if I apply this mask and multiply all these values and try to get the output value of that guy, then you reuse one of the real values for the output. So maybe that value should be computed. In which case, this value should be part of the outputs of your convolution. So you end up with a bigger picture. So anyway, so this is kind of arbitrary decision, and basically what you can do is you specify, say in MATLAB, you just say that you want the output to be of the same size as the input. Okay, so you say, I just want to make sure that the output of my picture will be the same size. All right, so usually when you apply for any kind of useful application, you will have this kind of command where you say, I want the output picture to be the same size as the input picture. Right. So, so this is what it's about. So this is what we say. Okay, so usually filtering is defined this way. Okay, so you have this little masks that we say are applied, and basically think of this mask as centered in a particular location here. So that'll be your central current pixel of consideration. And when you show this mask, that basically that you say I could take 4 times the current pixel minus the the sum of all 4 neighbors, so north, south, east, and west neighbors, right? And in the form, that would be, I would say, like a blur. So you take a weighted average of neighboring pixels and so on and so forth. Now, sometimes you have even size masks, and basically what you need to do is you need to specify and say which one you need to mark it and say, actually, maybe this pixel is actually the central pixel and corresponding to your current value. So this needs to be enforced. Now, 99% of the case, you'll be dealing with symmetric masks of this shape, 3 by 3 or something like that. So you don't have to worry too much about this kind of even size filters. Right, so it's a minor point again. By convention, okay, when you do convolution, the definition of your mask is mirror and flipped between the definition of convolution and the way you think about it, okay? So, coming back on here, this is a definition of a convolution. And remember, this is, this is the input coordinate you're looking at for the picture, and this is how you approach it for the weights. And remember, there's a flip going on here. You say it's h minus n1. And the reason we have that is because of the maths and the convolution and so on, Fourier transform and whatnot you have after that. But here, because of the minus sign, that means actually the weights are, definition of the weights is kind of a bit funny. It's kind of not the natural one. So, in theory, when you present a mask like this, the number you have here, -1, corresponds to actually the neighboring pixels not on the right, but actually the neighboring pixels on the left here. All right? It's a bit of a funny one. And the same here, if you take this guy here, you would think naively that the definition of this mask means that -1 corresponds to the weight you have associated to the pixel on the top, but actually no, it's the pixel associated to the bottom, okay? Now, everybody does this mistake, and even people publishing papers don't worry too much about that. And I said, in 99% of the case, your filters, your masks are nice and symmetric like that, and you don't have to worry about that, okay? So in practical terms, this is rarely an issue. I just want to flag that to you, so it's kind of something that can happen when you're trying to debug something, you wonder what's going on. That's what's happening here. Right, so, okay, so what we've seen, we've seen the definition of linear shift invariance, which is just an extension of linear time invariance, and we say that the natural operation that will yield that is the convolution, and so we've seen how we define the convolution using the masks and so on. So a few properties of the 2D convolution, very similar to what you've seen in 1D, is like it's commutative, associative, and distributive. Okay, so you can basically shuffle the operations as you would like them to do. Okay, so if you do, if f and yeah, so one example of what's going on here, for instance. Okay, so if you have two operations or two convolutions back to back. So for instance, one could be you apply a blur, and the second one you apply edge detection. Okay, so you could say here it's the same to do. I apply the blur first, and then I apply on the result of that the convolution on the edge detection for difference. Or you could apply first the edge detection and then follow that by the blur. Okay, so all this kind of works the same way. Anyway. Right, so there's a lot of text here, but basically, just to say that convolution by itself is quite heavy. Okay, so if you have, so let's say you have an input picture, okay, of size n by m, so that's the number of rows and columns, and then your mask is of size R by C, okay? Then, so you have say a 3 by 3 block, so that'd be R3 and a C3. Then the number of operations you have to do is basically the number of pixels you have times the number of elements you have in your mask. And that can become quickly quite large, okay? So if you have just a small picture, so PAL resolution, so a small picture, 576 by 720 pixels, then if you have an 11 by 11 mask you apply for every single pixel, a bit the same way that we showed the blur function at the end, then when you apply this mask at every single pixel, you have to compute what the output of that pixel based on the local neighborhood is. Then what you get is basically 50, the order of 50 mega operation per frame. That's quite a lot. So it's not trivial, okay? And that's why if you want to do these kind of operations, very quickly you run into hardware issues, or you want to use accelerated hardware, so you want to use GPUs or specialized DSP on ASICs chips and so on. Okay, so very quickly when you run into video, that's why you need accelerated hardware, because even so the operation per pixel is quite simple. To do that on every single pixel, because you have a lot of pixels, it is very slow. Right, we're going to stop here, and we're going to leave that for tomorrow.